All right, we're going to get into exponential decay, which is very similar to exponential growth, except with decay it goes down, right? Growth goes up, decay goes down. I think that makes sense. All right, so Amy is microbrewing, right? Root beer. Nice. Go do it, girl. Okay, so we've got elapsed time and the height of the foam. We want to figure out absolute and relative change based on the data given. Recall, absolute change is new minus old. Relative change is new minus old divided by old. So let's do the first one together. So when we are talking about the foam, we want to know this on the foam, not necessarily the elapsed time. So absolute change for the first one, 8.93 minus 10.5. I get, what? Hold on. Sorry, I had to erase my answer. I wanted to make sure it was right. So when I take 8.93 minus 9.5, I get negative 1.57. Okay, so now we know that that's on top, and I divide by my old value, which is 10.5, and that gives me negative 0.15, which is negative 15%. Okay, hit pause, finish out the rest of this table, and then we'll come back and talk about it. All right, so you'll see every 10 seconds, right, based off our elapsed time, the absolute change differs, right? It doesn't go down by a constant amount every time, but the relative change does go down, right? We have a constant decrease of 15%. And remember, it's okay, right? We're comparing based off the old value, which is why this is the same, even though our absolute change is different. So let's look at the next page here. We can talk about our model. Remember that your model for exponential decay is very similar to your model for exponential growth, in that you start with your original. Well, what was our original height? Well, it was 10.5 centimeters. Oops, forgot my decimal. 1 minus, what was our decrease? And we said our decrease was 15%, which as a decimal is 0.15. So our decay factor, remember your decay factor is found by taking 1 minus your percent decrease, and so I get 0.85 as my decay factor. If you multiply something by 0.85, your answer is going to get smaller, right? That happens. Okay, so my model, I like to use y because it just makes me happy. 10.5 times 0.85 to the x, where x is 10-second intervals. So when you're talking about 2 minutes is 120 seconds. So at 10-second intervals, that means x would equal 12. Because divide 120 by 10 and you get 12. So my exponent is going to be 12. So y equals 10.5 times 0.85 raised to the 12th power. Now remember again, you've got to do the exponent first before you multiply by 12. But it should be 1.49 centimeters will be the height of my foam. And if you look at this, I mean, this is at 90 seconds, then we'd go 100, 110, 120, 1.49. Yeah, that makes sense with what's going on. Sometimes it's good to just check, you know, whether or not it makes sense logically. Can Amy expect this model to continue indefinitely? No. Think about, I mean, maybe if you haven't drank root beer, you've seen somebody drink root beer, foam goes away eventually, right? So because it goes away eventually, you it's not just going to keep going away by 15%. Eventually the trace is not there and you're just going to have nothing. If Amy were to change her formula from the previous example to produce a longer lasting foam with a decay factor of 0.97, so that goes inside here. How could she calculate the percentage of foam that dissipates each interval? So now our model would be y equals, she's still starting with a 10.5 centimeter foam, but now her decay factor is 0.97 raised to that 10-second time interval, right? Or you could use x, whatever. What would her new percent decrease be? Well, remember that your decay, there we go. Decay factor is 1 minus the percent decrease. So her decay factor is 0.97. So 1 minus what is this value? If you subtract 1 from both sides, we get negative 0.03 equals negative x. That means we have a 3% decrease. Right? Because, and you can think about that, 1 minus 0.03 gives us 0.97. What do you add to 0.97 to get 1, right? That kind of concept. All right, last one of this page here. We have a model, y equals 20,000 times 0.88t. First of all, determine whether this is growth or decay. Well, if you look inside here, if it's less than 1, it's decay. right? Because that if you multiply something by something that's less than 1, your number's going to get smaller. So they say take away 1 from it, and you get negative 0.12. Because it's negative, we have a decay model with a decay factor of 0.88. Okay, so always just look at that number in there. If it's less than 1, you have decay because things are getting smaller. If it's bigger than 1, when you multiply by something bigger than 1, your number gets bigger, and that's where you have growth.